I'm Michael Crawford. I'm CEO of the Soil CRC, and I'd like to welcome you to today's webinar. I'd like to begin by acknowledging the traditional custodians of the land on which we meet today, wherever we are in Australia or internationally, and I pay my respect to their elders past and present. Today's webinar is looking at recovering nutrients from organic waste streams to be delivered by Dane Lamb of the University of Newcastle. And quite fortuitously, today's webinar is quite relevant because today is Global Fertiliser Day, in case you didn't know. It's the anniversary of the invention of the Haber-Bosch process, which essentially was responsible for giving us our nitrogen fertilisers back in 1908. And so it's the Haber-Bosch process and the invention of nitrogen fertiliser that is notionally responsible for feeding 30, 40, 50, 60% of the global population today. Before we get into Dane's presentation, recognising that the attendees today, we have a range of participants, some who are quite familiar with the Soil CRC, some who do not know too much about the Soil CRC. I'll say a few words about it. CRC, the Cooperative Research Centre for High Performance Soils, was established in 2017 with funding for 10 years from the Australian Government and its partners. We have 40 partners, 40 participants, universities, state government agencies, industry groups, and importantly, 20 grower groups, farm groups from around Australia and from New Zealand. We've been established to undertake research to help give farmers the tools and knowledge they need to better manage their soil and improve their productivity and profitability. So you can find a lot more about our Soil CRC on our website, which is listed there at the bottom there. We have a series of upcoming webinars. This is part of our ongoing webinar program. So a little advertisement whilst waiting for others to come on. 27th of October, in 2 weeks' time, we have Dr. Mahan Reza Rashti from Griffith University looking at soil functional resilience to compaction and drought stresses. In early November, 10th of November, David Falapau from Charles Sturt University talking about building farmer innovation capability and some of the work he's been doing with grower groups and staff of those grower groups to help build that innovation capability and embed it within our participant organisations. And then on the 24th of November, just released details about the webinar from Liang Wang at the University of Newcastle, and his colleagues are Ruben Ma and Fernando Mayer from University of Tasmania, looking at affordable, rapid field-based soil tests, or the lab on a chip technology that's been developed within the CRC. So you can enrol for and register for each of those webinars through our website in the same way as what you've done for this one. So back to today's program, Dane Lamb. Dane is a Senior Research Fellow at the Global Centre for Environmental Remediation at the University of Newcastle. He has a Bachelor of Science from Griffith University and a PhD from the University of South Australia looking at heavy metal phototoxicity. And he's leading a project in the Soil CRC looking at this topic of recovering nutrients from organic waste streams. It's been going for a little over a year. So Dane's talk today will speak about the research in progress and what they've found so far. Just a couple more housekeeping aspects. The webinar is being recorded such that we can view it later on our website. You can review it, or you can let your colleagues know and others can review it at a later date. Within a couple of days it'll be up there. You're welcome to enter comments into a chat box at any time. In terms of questions, there's a Q&A box. Type your questions into the Q&A box, and after Dane finishes speaking in about 25 minutes time, we'll then start reading out the questions in the Q&A box. So sit back and enjoy. Dane Lamb, thank you.
Hello, everybody. Welcome to our webinar. I'll share my slides with everybody. Hopefully everyone can now see that. Okay, so yes, thank you, Michael. Yeah, the project has been going for a little while, all about making the best out of nutrient and organic waste streams. The project in general does involve many different nutrients. We are aiming for nitrogen, phosphorus, calcium, sulfur, and etc. However, the big focus so far, and the primary focus in the project, is in phosphorus removal from the waste waters. So one of the large reasons for that is the relative low phosphorus availability in Australian soils. This is obviously not the case for all soils around Australia, but as a general principle, that is quite often the case. This largely occurs because of our strongly weathered soils and our large amount of iron and sesquic oxides. One of the really big driving forces for phosphorus is because it is primarily sourced currently from phosphate rock material. Unlike nitrogen, which Michael's just mentioned in relation to nitrogen, we are unable to acquire almost unlimited amounts from phosphate rock. So it has been sort of widely reported that over the next, depending on your numbers and your perspective, phosphorus from phosphate rock will start to decline. And as that starts to occur somewhere in the next, say, 15 to 100 years, we will have issues with keeping the productivity of our soils, particularly in areas and continents such as Australia with a very high absorption ability in our soils. So around the world, phosphate rock is produced at really large amounts. An estimate is something in the round of 230 million tonne per year. In Australia, that is obviously much less than that is used. The total quantity, however, from all of our organic waste streams is something in the range of 5 million megagrams or tonne per annum. So this is an enormous resource that is currently available and used to some degree, but not as efficiently as we would like. This is approximately around 20 times higher than the current agricultural demand. This comes from different wastewater sources, including there's a very large amount that is sourced from manures. In the US, this is up to 2 million tonne per annum produced from livestock manure. But there are also many other waste streams, apart from your piggery, chicken farms and dairy effluents. There's also a major phosphorus load that is can potentially be sourced from our wastewater treatment plants. One of the downsides of also not capturing as much of our nutrient as possible, apart from the loss and potential productivity that we could be utilising, is the potential for runoff and also surface water eutrophication, which most of us are well aware of as a significant issue. So in terms of the project, our major aim is to develop either fast or slow release fertilizers derived from these wastewater streams, and that does include different wastewater such as potentially sugarcane industry, the dairy, piggeries, chicken farms, and also our wastewater treatment plants, and to turn these into products that are useful in a range of Australian soils and Australian climates. So the project is broken into different stages. We are currently in the component where we're trying to develop technologies that can remove phosphorus from these wastewater streams into forms that are useful, which means essentially phyto-available to plants in different soils. One of the first challenges, however, in doing that is to be able to effectively capture the phosphorus in the appropriate form, which is quite difficult and has been attempted for quite a long time. So the techniques that have been employed to date are vast. These generally include chemical precipitation, which is the formation essentially of a granule, adsorption, biological removal in different, for example, algae as a potential option, membrane techniques such as forward and reverse osmosis, pyrolysis of sludge, and there are also electrochemical approaches. And there are also going to be, in addition to these, some other minor technologies that have been trialled currently. However, of all of those approaches, one of the most studied and most easily utilized is the adsorption. And this is the use of solid materials to effectively bind from the wastewater stream and to concentrate these. So there are many potential useful adsorbents, and the number of adsorbents for many chemicals, including phosphorus, are vast, and these can potentially include a range of nanomaterials, oxides, double layered hydroxides, and there are an enormous number of modifications currently being trialled in the literature. The project is looking at adsorption processes as a viable option. However, the primary focus is in the development of a salt or a fertiliser product at the bottom, and this is going to most likely involve a precipitation process. So although this slide looks a bit complicated, basically the idea is to design a system in which we can effectively remove a designed material. So this is, our aim is to use what we call a nucleation approach, where we develop essentially a seed which we can add to a wastewater that can basically precipitate the desired salts. There are different types of nucleation, and if you're interested, you can look into these. However, I won't go through those in a great deal today. So in terms of the projects, due to the many different wastewaters and many different technologies available, we've tried many different approaches as well. So we can break these into 4 different categories. Pure minerals. Now these are essentially adsorbents, and we're not proposing that these will be used as a final product that can be then added to the soil, but more of a way of capturing the phosphorus and nutrients in the first instance, and then developing a fertilizer from there. The second, which is our primary focus, is the calcium magnesium phosphates, which we'll talk about in a minute, which include different forms such as struvite and different apatites. More novel is the area of bead adsorbents, which is again a bit of a mix of B, which we'll talk about briefly. And finally, something that I think a lot of people have heard of, and that is biochars and the potential modification of the different biochars. So just to give a bit of an idea of what the nucleation process is and how it is designed, we need to develop a solution. In our case, we plan to develop a more concentrated solution using membrane approaches to remove some of the water to concentrate. From there, what we are currently doing is developing a form of crystal. So some of the precipitation processes will occur, but they may occur a bit slow and they may proceed in different directions. So what we want to do is, first of all, accelerate that process, and we also want to move it in a direction that we design. So that involves the addition of a pre-designed cluster, which we would then add to our solution. From there, it's basically starting the reaction, and then we have the crystallization around our seed. From there, we can form different amorphous or slightly crystalline minerals, and with time, these develop into fully formed crystals, which would hopefully in the end be our product. This is an example of a carbonated apatite. Now, the nucleation and crystallization process is dependent on many different factors. In terms of the development of our different types of apatites, the ratio of calcium to phosphorus is very important. Also, the pH, as always with any sort of inorganic chemistry, is essential. But there are other factors that can also influence the success of our approach, which involves the presence of foreign ions such as organic acids or heavy metals, and also obviously pH and atmospheric conditions. So one of the main materials that we're currently trying to develop is the calcium phosphates. This in one instance is a nanohydroxyapatite. So this is a transmission electron microscope image of some of our hydroxy nanomaterials that we have developed to date. As you can see, we have developed in the nano range, which is what our aim is, and this is actually a very good particle size range. A lot of literature is actually much larger than this. Now, obviously our hydroxyapatite or hydroxyl apatite is very soluble at a low pH, but it may be a bit of an issue at high pH in terms of solubility and maybe more of a slow release. So we have also tried to develop modified forms of hydroxyapatites which will have higher availability when they're added to soil. Now, in the literature, one of the primary minerals that are being used to sequester phosphorus and recover it from wastewater streams is something which a lot of people may have heard of called struvite, which is the common name essentially for an ammonium, which is a nitrogen form magnesium phosphate. Now, these is in fact a problem in some wastewater streams because it forms scales and clogs up different infrastructure. But in terms of phosphorus recovery, it is beneficial because it is relatively easy to recover. So we have developed some struvite recently, and we have also trying to develop different forms again of the struvite and trialing different conditions that might affect the struvite crystallization. And as you can see, this is an XRD spectra. We've managed to form some struvite, and in our calcium enriched waters, we've formed two minerals, which is struvite and bruchite. Struvite is a little bit of a controversial mineral as a fertilizer. It has several potential issues. One of these is the potential for concentration of arsenic, which is not desirable and can be at levels much higher than what we'd like in our agricultural soils. But in addition, it is also has very low solubility. However, in some way, this could be marketed or used as a slow release fertilizer. But one of the big benefits, as I mentioned, for struvite is that it is relatively good at recovering phosphorus from wastewater. In our work in the laboratory so far, we have managed to recover, under optimal conditions, I should say, nearly very close to 100% of phosphorus in the waters. So this is obviously the main benefit and very promising. Now, in addition to hydroxyapatite and struvite, we have also developed or trying to develop another mineral called bruchite, which is again a calcium phosphate, but will hopefully be more soluble than hydroxyapatite, which also has a constraint of having relatively low solubility. This is just to point out that there are many different forms of apatite and you can modify them in many different ways. So this really is one of the big reasons why we need to use seeding approaches and sophisticated approaches in order to develop our fertilizer products, because we need to be able to design and manufacture reproducible and reliable materials. So as I've mentioned, we are also looking at sorbents, and again, this is not proposed as something that we're going to be adding to soils, but as a way of concentrating the phosphorus to develop our products. So materials that we can use and reuse potentially have very high affinity for phosphorus. So materials that may potentially be used are zirconium and rare earth elements, which have very high affinity for phosphorus. So we've developed a range of these different materials, which I will come back to in a second. So also we have developed some materials which are called alginate beads. Now the main benefits of an alginate bead is firstly to embed our highly reactive materials in an efficient way, but also in an environmentally efficient way. So alginate tends to be produced from algae, so multi-cellular algae such as seaweed. So it is based on a environmentally friendly and non-toxic form. So what we do with the alginate beads is that we are able to embed our reactive materials, whatever they happen to be, inside this material that can then be used to recover phosphorus or other nutrients from wastewater products. So we have used some innovative ones there where we use a small amount of a rare earth element with a relatively large amount of magnesium and iron, but we have also been trialed a range of calcium alginate beads in order to recover more calcium phosphorus minerals. So this is effectively going to work very similar to our crystallization pathway, where we have our calcium phosphate seed embedded in our non-toxic alginate beads, which we can use to, again, recover phosphorus. This is very much in our developmental stage. Now, as the fourth and final material that we were working with and trialing in the lab is the development of biochars as a means of recovering and distributing to soils. So biochars, for those who aren't aware, is a material that is proposed as a highly resistant, slow release form of fertiliser, but it's also proposed as a way of sequestering carbon that would be much more recalcitrant to degradation over time and has a benefit of removing some carbon from the atmosphere. But it does have many other properties apart from the carbon sequestration, in that it also captures a lot of the nutrients in those different forms. So there is a lot of work on using biochar for different nutrients. That includes essentially anything that can be in a organic biomass such as sugarcane or manures or biosolids. So they essentially capture most of the nutrients. Now, one of the big questions about biochar though is when we do this, and this is through a process called pyrolysis, we are making materials that we, in some cases, don't really know what's transforming into. So in the case of phosphorus, when we do our pyrolysis conditions, we can form, depending on the feedstock and our reaction conditions, we can form many different forms of phosphorus, which will have many different availabilities to plants once we add them to soil. So in general, what we have been using a biosolid biochar, which does tend to have a relatively large amount of inorganic fraction. So this is the case for many different biochars. It's not the case that it's organic. A lot of the forms are in fact inorganic forms. So in our biochar, which we have pyrolyzed at 400 degrees Celsius, we have managed to get this material to Taiwan, to the Taiwanese synchrotron, and have a look at some of the speciation in our materials. So what we have on the right is the spectrum, and on the bottom two, we have our biochar and our calcium modified biochars. The top are basically standards, which we have fitted to that data. Using this sophisticated approach, we have found that by and large, our unmodified biochars are essentially iron phosphates, which is potentially not very available. And in addition, we have also formed in some conditions hydroxyapatite and also magnesium apatite, which is much more favorable. However, these tend to be in lower proportions. So what we wanted to do is also to produce a biochar, but then to try and recover more phosphorus and other nutrients from the biochar once we form the biochar. So in the first instance, we've tried an adsorption process due to the high mineral fraction. And what we have found is the biochars, which actually have very large phosphorus, in our biosolid biochar, which is BSBC, we have around approximately 5% phosphorus, which is a lot. So when we try to sorb phosphorus to this material unmodified, what we find is, in fact, there's a net release of phosphorus. So when we add phosphorus, instead of sequestering more, we're actually just losing phosphorus. So what this means is obviously it's not going to be an efficient process without any modification. So we have trialed different modifications. Again, we have tried iron modification on the graph to the right. And as you can see, we've gone from a net release to at least recovering some phosphorus net adsorption to our biochar. But when we dope our iron modified biochar with a small amount of zirconium, what we can see is a much greater removal of phosphorus from the biochar, which gives us some avenue for greater removal. Like I said, we have tried many different modifications for this, and I won't go through this in detail as we're getting a little bit low on time. But we have tried calcium doped, but we saw earlier that that did not sequester much phosphorus. So we are looking at essentially iron and aluminium based modifications of the biochar in order to recover more of those materials. And there are also magnesium aluminium biochars, which we'll get to at the end. So as a comparison to some of the more, let's call them novel materials, we have tried, so this is our phosphorus sorption with our biochar. But what we can see here is that we can get much greater removal. And one of the other problems with our normal biochar is relatively slow reaction kinetics. So when we modify it with our aluminium, iron, or rare earth elements, what we find is, number one, much greater sequestration, but number two, much faster reaction kinetics. Some of our biochars may take up to 3 days to get to equilibrium, as pointed out here in the bottom of the right graph, which is far too slow for a process. So again, what we've done is we've modified some of the materials, and then we wanted to know what form did they transform into. Again, from Taiwan with XANES, we have developed a zirconium loaded biochar, which was an effective removal technology. The main point here is that we still have a large amount of iron and magnesium phosphate, but we've actually now developed a surface adsorbed zirconium phosphate. And similarly, with our iron rare earth modified biochar, we still have a lot of predominantly iron phosphate biochar in the end, which is good to know and important to know once we are talking about how bioavailable these may be in an experimental setting. So in addition, like I said, we wanted to recover, the first step is to recover the material. So one way is to use an adsorbent and then to sequester it as most efficiently as possible. So we tried 2 hydroxide materials to concentrate the material first. One is our zirconium hydroxide and zirconium oxide minerals, and also yttrium hydroxide. So what we know from the literature and what we found as well is that zirconium is probably a far more useful material in terms of recovery of phosphorus. Now, the primary reason for that is in the red, what we can see is once we can recover a lot of phosphorus at a low pH, and then what we can actually release that into a form that we can then reuse if we desorb that with a base. But in terms of the rare earth elements, there's a much stronger retention with the phosphorus. So regardless of the pH, in the case of yttrium, we in fact got essentially 100% removal in all pHs. So what this would mean is that in the first instance, we don't know, we haven't got yet a process to effectively recover that. So this may be much more useful as a material in a setting where we just want to remove the phosphorus, for example, preventing eutrophication in the surface water. Some of our other materials, such as the cerium hydroxides, were even far too inefficient. We have also trialed different conditions, and in some cases we get improvements in our removal. So we wanted to try and see if we could develop using surface-induced precipitation of some calcium magnesium phosphates. We did get some improved sorption from that, but based on our XANES data from Taiwan, it doesn't look like we've really manufactured the material that we were hoping for from that approach. So finally, we have also looked at magnesium aluminium biochar, which is something which is far less exotic and perhaps more amenable to soil. So we have modified it with an aluminium magnesium biochar, and based on XRD, we haven't been able to take this to Taiwan as yet. We've been able to form some aluminium and magnesium based materials using this. So that's the last of the materials that we have developed. So that's a lot of chemistry. As Michael said, we are in the first phase of our project, where the first step is to find the best way or an efficient way of removing the nutrients from the wastewaters. So what next? So we've screened a lot more materials than what we had originally planned. We originally had a streamlined approach, but we've tried many different materials. What we're now going to be doing is screening the plant availability of the phosphorus in the rhizosphere, and also we'll be trialing this in a very sort of rapid way through a range of soils as well. Moving on from that, from the screening process, we're going to develop, do the testing in the greenhouse and then into the field finally. So by doing this multiple screening approach with multiple materials, we're hoping to identify the most suitable material that can finally be manufactured at a larger scale from organic waste streams for the recovery of phosphorus from wastewaters. So I need to acknowledge everybody who's involved in this project, Griffith University, Southern Group, Cross Universities, other research providers. In addition, we have a number of industry participants, SE Water from Melbourne, PERSA, David Davenport, Helen McMillan from Southern Central West Farming System, also Landcare, Professor Sagar from Land Research, and also Lawrence, and David Bonza from Aora. And also need to acknowledge Dr. Anita Kunikrishnan and Amanor for providing the data for this talk. They're the driving force behind this project. So thank you.
Thank you very much, Dane. And there's Dane's email for you to be able to address issues and questions to him afterwards. So we're open for questions now. However, I don't see any questions in the question and answer box. So please type away into the Q&A box, which should pop up at the bottom of your screen when you hover your mouse down there. In the meantime, Dane, here's a couple of questions I prepared earlier. Can you talk about what's happening internationally in this area? The potential and the opportunity for recovering phosphorus from waste streams is not a uniquely Australian one. Is there research and development relevant to this issue in other countries that we can speak of?
Yes, most countries are working on this problem as well. In particular, there's a lot of work in particular Europe in terms of developing industrial scale processes for the recovery of phosphorus. To my knowledge, that is largely going along the struvite pathway. Similarly, US is also very active in this area as well, and that's a big country and they are doing many different things across the country, but struvite again is a very important path for US as well. A lot of the research is also very much involving preventing eutrophication. So not so much making a fertiliser product, but actually just stopping phosphorus getting to wastewaters.
Thanks.
So
Thanks.
it is definitely an international problem. I think it's most countries are trying to develop approaches for this.
Yeah, good. Thanks, Dane. And so with that time, some of the questions have started to come in. So Jeff Cracker's asked, yeah, can you elaborate on the arsenic risk with struvite? When you spoke of struvite, you spoke about the high levels of arsenic. Can you elaborate on that risk?
So even because we're concentrating material, when we concentrate the phosphorus, we also get even trace amounts of arsenic into the struvite. So the literature shows, unfortunately, that quite a large amount of arsenic will in fact get incorporated into the struvite structure. And it doesn't matter, unfortunately, what is the form of arsenic, which is the problem. There was originally an idea, perhaps if we, instead of having an arsenic form that's very similar to phosphate, if we were to reduce that to have a different electronic structure that was less similar to phosphate, then we could avoid its inclusion in the struvite structure. But the literature has shown that, in fact, regardless of the oxidation state of arsenic, we still get significant incorporation of arsenic into the struvite structure. The literature indicates something in the range of 200 to 500 ppm of arsenic, which is much higher than what we're currently using. And definitely EPA would have some interest in that sort of level of arsenic as a fertiliser product.
So is it a showstopper, Dane, or is there the ways we're going to address this?
Well, one of the ways of getting around struvite has been also to dilute it with other more soluble fertilisers. So we can still recover the struvite and then mix it with, for example, rock phosphate currently, because that's much more financially viable, and also water soluble. So some of the literature recently indicated that's sort of a design of a fertiliser. We can use a very soluble fraction with struvite, which is slow release. So we can get some bang for buck initially, and then we have a slow release of phosphorus. That would have the benefit of also diluting the arsenic. But unfortunately, if you keep doing that, eventually it will build up in soil, because unfortunately arsenic will get extracted a little bit into the plants, but it's basically not going very far.
Right, thank you. A question from Nancy Boland. The concentration of phosphorus in the waste stream is very low, which is a challenge in recovering phosphorus from waste streams. From your experiments, which approach is efficient in the recovery of phosphorus at low concentrations?
Yeah, so we can, so far, definitely the best material that we've found is yttrium. But the problem is getting that phosphorus back off the yttrium oxide. So it looks like that probably in fact is precipitating an yttrium phosphate. So the best material in terms of being able to reuse it so far is to use zirconium, where we can just desorb that at a high pH for concentrating. But we are also developing an approach for concentrating the solution so we can then just precipitate the materials that we would like. So we don't have a direct answer yet, which is definitely the best, but those are the two approaches that we're going with as the preferred options.
Okay, thank you. A question from Chanrat. What type of wastewater are you trying to recover the phosphorus from? I guess a follow-up is, and how variable is, or how dependent is this on the type of wastewater?
That's it. We are trialling, so far we've sampled from the different suppliers, domestic wastewater from Melbourne, dairy effluent, piggery effluent, and winery effluent. And we're also trying to get some from the sugarcane industries. Nancy's right, typically the concentrations are not enormous, but the amount of phosphorus is high due to the volumes. So we do need to concentrate it, and there is variability, of course. So, for example, in the better documented materials such as the municipalities, they tend to range around 10 ppm, and that's relatively consistent. But there's obviously going to be fluctuation based on season, the amount of water that dilutes the feedstock. So this is where a process is important for unifying that and concentrating the solution.
Thank you. A question from Baba Biswas. Can you please give some thoughts if there is any modification or treatment method that could potentially remove or reduce the arsenic content from the stuvite structure impurities?
Yes, that's a good question. So one of the PhD students in Newcastle is trying to find a way of selectively removing arsenic from the wastewater because they are very low levels. So it could be a viable way before we do our struvite precipitation step. So that's a good question.
All right, so I think we have come to the end of the questions that are in the box, and I'll just sort of pad out for another 30 seconds or so if there's any other questions. Yeah, thank you. So Tony Paddy has asked, are you looking at any solid organic wastes, or what's the future research directions in that space?
It's a good question. It's one that I get asked quite often. Yeah, it's obviously a very important waste stream. We are working with biochars, but it's not a big component of the work. We're more using it as a feedstock to recover more phosphorus from the waters. I think other projects in the CRC soil are looking at using the solid feedstock as a phosphorus source. So it's not a large focus in our project.
If you were to do this at solid waste such as manures or compost, etc., what would be some of the technical challenges that would make it that different?
So uniformity, there are problems with organic feedstocks in terms of obviously microbes, but there are many processes that get around those. But you need space and you need to pile that material up. And to my knowledge, and I'm not an economist, so I can't speak too much on this, but I believe delivering very light, low density material distances to distant and remote farming areas is a major limitation on the use of solid organics. So one of the benefits of developing a salt is that you have a lot of nutrient dense material that can ship at a more affordable price.
Yes, or if you can apply such a technology close to the source and then you're transporting the concentrated nutrients rather than the large bulk, low concentration of mass. A quick question from Baba Biswas. With increasing P concentration, any of your materials showed rather low sorption capacity?
Some of the less efficient materials do, such as the cerium, which was not a very efficient material, but in general, no. We get, certainly in up to a high concentration range, we get very, very good recoveries. As I showed with our solids and our absorbents, we're getting very close to 100% removal. So currently quite beneficial, but we do have to try and make sure they work under different conditions as well, because for the different wastewaters that we may encounter.
All right. Thanks everybody for your questions, and thanks Dane for your presentation, taking us into the science of what's going on here, and we're demonstrating we've taken quite a deliberate and sophisticated technical approach to investigating and potentially finding a solution and addressing these issues. So thank you very much. Just to finish off then, a reminder about those webinars that are coming up in future weeks as part of our ongoing program. You can find all the details at our website at soilcrc.com.au. Also, I encourage you to follow us on Twitter, connect with us on LinkedIn, and subscribe to our YouTube channel where you can also see this webinar and all our past webinars as well. So thanks again, everybody, and enjoy the rest of Global Fertiliser Day.